Hello, everyone. Welcome to Chapter 3. My name is Gwen from EveCom Quantum Systems, and today we are going to look at quantum computation. In the last chapter, we established the four postulates, the fundamental laws of quantum mechanics. Now, we build the architecture. This chapter is about quantum computation, how we build the circuits and prove that our minimal set of tools is actually powerful enough to run any algorithm imaginable just based on the four postulates. So let's start with the blueprint, the circuit model. Think of a circuit as a timeline. Qubits travel from left to right, and their state is modified by a sequence of gates, very known like the CNOT. So the critical rule is that the entire circuit, from the first gate to the last, is just one large combined unitary transformation. But we have a constraint. Classical non-reversible gates like NA and D cannot exist here. Because your gates are unitary matrices, they must be reversible. So we can't just start processing data. We need to actually perform a reversible dance or exchange. So this is the minimal toolkit. We can't build an infinite set of gates for every calculation. We actually need something called a universal gate set. The breakthrough discovery is that you don't need everything. The combination of all single qubit gates and the controlled CNOT gate is actually a proven universal set. So this is the compiler for our classical to quantum bridge. You've got your high level intent, your algorithm, and it gets decomposed into these two machine code instructions, single qubit rotations and C-naughts. And thanks to the Solovay-Kitaev theorem, we know that we can approximate any complex gate with incredible accuracy using a list of discrete gates that don't explode in size. So this is where engineering meets theory. We have four key metrics to decide if a circuit is actually viable: time, space, gate, and error rate. So the depth of the circuit is time or the number of steps. Space is the width, how many qubits we need. Gates are the total size or the number of operations. And error rate is the most critical resource where if our gates mess up faster than we can correct them, then the circuit fails. So we must keep this below a very specific threshold. So we're taking a look at the simulation challenge of Trotter. This leads us to Feynman's insight. Quantum mechanics is the only efficient way to simulate quantum mechanics, but the math is brutal. So to find the state of the system, we need to calculate e to the power of IHT, a giant impossible matrix. The trick to solve this is the Trotter decomposition. We split the Hamiltonian into many simple terms and cycle through them in small time steps. It turns an intractable calculation into a series, a sequence of simple buildable gates. So it's the core of how we simulate molecules and materials. And so now we talk about QFT, the engine of speed up. And remember, guys, this is a very, very top level explanation of all of these terms. I do hope that you take the time to kind of take a look at the notes that we'll provide. So we'll just arrive now at the engine of quantum speed up. We're talking about the quantum Fourier transform or QFT. So think of the QFT as a phase to amplitude converter. So in many algorithms, the answer is hidden in the phases of the qubits where we can't see it. So the QFT takes the unobservable phase information and rotates it into amplitude information, making the hidden layer measurable. It's the ultimate feature engineering tool for quantum state. So we've moved essentially from abstract rules to actionable architecture. We have a toolkit, we know how to measure costs, we can simulate physics, and now we have QFT to extract the answer. But we still have a question. How do we actually program these to get an exponential speed up? And this brings us to chapter 4, where we talk about the strategic use of interference and phase kickback.